Alright, find the volume of the area between the functions f(x) equals square root of x plus 3 and x equals 1 is rotated about the x-axis. The first step of all of these problems is going to be to make a graph, so let's go in and do that. Graph both the square root of x plus 3, which will start at negative 3, and should curve up plus 1, then plus 3, 1, like a square root graph, and keep going. The other one, x equals 1, which would be a straight line, and x equals 1. Alright, up there. Then, so the area we're looking for is this section in here highlighted in red in the middle, and that's going to be rotated about the x-axis, making a sort of a spherical cone sort of shape, right there. This will be a 3D shape, though. Go all the way around and cover all of this areas. So now we need to set up an integral. Our cross sections are going to be of x. Go down here. So the first thing we need for integral is we're going to need to find the bounds. So, first we need the pi. We're going to have pi times the integral, which will be the bounds of the functions on the x-axis. So negative 3 is where we start, where we touch the x-axis. And then the ending is going to be where it intersects the other function at x equals 1. You want to look for the intersections of the functions. Then for our volume, we're going to use disks. So that's going to be the pi r squared, but the pi is already drawn out of the integral. So we just need r squared. The r is the height of the function, which is root x plus 3. And then because it's r squared, we're going to square that. And then times dx, because we're going across the x-axis. X is our changing variable. So now let's simplify this integral. Pi will stay. We'll carry that down to the end. The square root and squared are inverses and cancel, so we end up with integral of negative 3, 1 times x plus 3 dx, which is a much simpler, easier integral to do, times pi still. So then let's simplify this even further. We'll plug in the values. We get 1 half x squared plus 3x, which is our antiderivative of x plus 3, and times pi, which are carrying down, and then the bounds are still negative 3 to 1. Now we need to plug in the left and right bound and subtract the two to get the value of the integral. So we will go down here, do 1 half 1 squared plus 3 times 1, and then we are going to subtract, in parentheses, negative 3 plugged into the antiderivative, so 1 half negative 3 squared plus 3 times negative 3. Alright, now we just simplify this down. We go 1 half plus 3 is 3 and 1 half minus 9 is negative 3 squared over 2, so 9 halves plus 3 times negative 3 is negative 9. 9 halves minus 9 would just be 9 halves. But that's also subtracted again, so it's going to end up being positive, and 3 and 1 half. And then we add the 2, we'll get 8. Plus 9 and a half. There's one more step after this. Once we add these, it's 8. We forgot to bring the pi down. We go bring the pi all the way down now that we finished. And multiply by pi, 8 pi.
So today the problem we have is find the volume when y equals negative 2x plus 4 and y equals x squared plus 4 is revolved around the y-axis. We'll just start off by drawing a graph, as Mr. DP recommends is necessary to have a good illustration. And all we're just going to be doing is plotting a few points, just getting a general gist of what the graph will look like. So this part will be y equals negative 2x plus 4. And then next I'll draw y equals negative x squared plus 4. And then I'll shade in red the little portion that is the area between the curves. And when that is revolved around the y-axis, that will be our volume. So as you can see, it says to be revolved around the y-axis. So our first steps are to set the equations in terms of y. You technically don't have to do this, but this just makes it easier to visualize based on the graph that we already have. So we'll just be doing some simple algebra. We'll just be moving the negative 4 over, dividing by -2, and eventually we'll just have -1/2 y plus 2 is equal to x. And then we'll just do the exact same thing to the other equation. So y is equal to -x squared plus 4. We'll just move the 4 over. Next step would be to square root both sides. Or, sorry, do the negative to the other side. Then you'd move the square root over. And then that's your two equations in terms of y. So we can start setting up the integral now. So we'll just do integral times pi, since it's the washer method. And our bounds are from 0 to 4. And so we'll just put that from 0 to 4. And we will do squared of the right equation minus the left equation. So in this case, the right equation is y is equal to -x squared plus 4. So we'll just square that in the integral. So here we'll just write squared negative, so we'll do square root of -y plus 4, because we changed it to be in terms of y. And then we'll just have -1/2 y plus 2 squared, because this is the left equation. And then we'll just have it times dy. And if you plug this into your calculator, you will get your final answer of about 8.378.
So let's look at this next problem. Find the volume when the area above y equals 1, below x cubed plus 1, and bounded by root -x squared plus 4 is rotated about the line y equals -1. So let's first graph this out. This is x cubed plus 1. This is y equals 1. And this is root -x squared plus 4. So, looking at the problem, it seems to be looking for this area right here, rotate about the line y equals -1. So first, to solve this, we need to find these two intersections. So to start, let's set these two equations equal to each other. So x cubed plus 1 equals root -x squared plus 4. So plugging this into our calculator, we get 0.9190619, comma 1.796321. So next, let's find the other point of intersection. We have root -x squared plus 4 equals 1. So also plugging this into our calculator, we get root 3, comma 1. So now that we have these two coordinates, we can set up an integral. So using pi r squared, using disks with another disk inside, we get pi times the integral from 0 to 0.919, the value above, x cubed plus 1 because we're rotating around the y equals -1 squared minus 1 plus 1 squared. And then we add this as well to our second integral because there are two different equations that bound this area. So pi, the integral from 0.919 to root 3 of the half circle equation plus 1 squared minus 1 plus 1 squared. So if we plug this into our calculator, we get 0.792619 pi plus 1.718111 pi. Now simplifying this further, we just get 2.511 pi, or we get 7.858.
Okay, so the problem reads, find the area of the region bounded by cosine of x and sine of x from x equals 0 to x equals pi over 4 when rotated about the y-axis. So the first thing I'd want to do is find out where these curves intersect in the first quadrant. So I would do that by setting them equal to each other. Okay. And if I think about it for a second, I realize that through the unit circle, there's actually a point that relates these two functions where they do intersect. And that point would be actually at pi over 4, because cosine of pi over 4 is root 2 over 2, and sine of pi over 4 is also root 2 over 2. Okay? So that would leave us with the point pi over 4 pi over 4, comma, root 2 over 2. Okay, why don't we take a look at the Desmos graph now, which I have here. We've graphed cosine of x and sine of x, and we can see at pi over 4 they actually do intersect, and the y value is 0.70711, and that's the same thing as root 2 over 2, essentially, okay? So now that we have this, we're going to find the area of it, this region rotated around the y-axis. So let me draw that region super quickly. Okay. And then it's going to look something like this, roughly. Okay, and then we rotate it around the y-axis, and it would look something like that. Okay. Okay, so I'm going to be using vertical disks. So if I draw one sample disk inside this region, it would look like this. If I can draw the disk correctly, sorry. Okay, perfect. So that's what the disk would look like, right? So in terms of solving for these disks, the area we can use, the formula we can use is the area of that disk equals pi r squared. And then, of course, the thickness would just be dy, but we'll leave that in the integral, okay? So the only missing in this equation, the only unknown in this equation is r. How do we find r? R is going to be the radius of these disks, or in other terms, the x-coordinate of these functions, okay? So how do we find the x-coordinate from cosine of x? We'd actually have to take the inverse of cosine of x. So we do cosine inverse of y to then find the value of x at a certain y coordinate, because we're doing vertical disks in terms of dy. Okay, and then for doing that, we can use sine inverse and cosine inverse. The thing we need to be careful about, though, is if we look back at the graph, there's a break right here, because all the way up till here, we're measuring the x values of sine, but the second we go above root 2 over 2, we're actually measuring the x values of cosine. So we need to factor that break into our integral volume expression, okay? So I'll draw the break right here. So just to make sure it's clear. Okay, so first I'll write the first integral, which is going to be pi on the outside. And then it's going to be by r squared. The function going from y equals 0 to y equals root 2 over 2 is going to be sine inverse of y. So I'm going to write sine inverse of y. That will give me the output of the x coordinate. And then I'm going to square it because the value it outputs is simply the horizontal distance from here to here, right? But we need to square that in terms for it to be in terms of the disk we're creating when it's rotated around the y-axis, okay? And that's going to be again from 0 all the way up until root 2 over 2, which is 0.707. Okay, and then we're going to add that because now we have the break point, right, where we're going to change the function we're working with by the same exact expression, except we're going to change the sine inverse of y to cosine inverse of y. Oh, and don't forget the dy. dy plus pi cosine inverse of y dy. Oh, cosine inverse of y squared, and then we'll add the dy. And just to real quick think again about what we're doing here, we're going from, in terms of y, we're going from the y coordinate 0 all the way up to root 2 over 2, and we're simply spinning a disk around the y-axis, and we're using the radius in terms of the circle area formula. And the radius is just going to be equal to the x value of sine at the given y value when we're going up. Okay, and then after the breakpoint, above root 2 over 2, until we get to 1, we're going to be doing the exact same thing with the cosine function, or, well, to find the x value, we're going to be using cosine inverse. Okay? And this one goes again from root 2 over 2 to 1. So let me add those bounds here. And that's it. That's the integral setup for the problem. You don't need to evaluate it, but if you want to check that you got the same answer, what I got on my side was approximately 0.696. Perfect.